the topic of shear strain and the relationship among the velocities during the cutting operation. I'm talking about the turning operation here. So this is the diagram you are familiar with, the single point cutting tool removing the material from this workpiece, which is having the relative velocity v with respect to this in this direction, and also known as cutting velocity. We can write this as vc also. So we will find first of all the expression for the shear strain produced. As you know that the material is sheared along this plane. This is the shear plane we have discussed previously, and there are more than three shearing planes. So two will be here. This is the primary shear zone, and we have the secondary shear zone along the rake surface of the tool, which is in contact with the lump of mass which is moving related to this, that is known as the chip. This is the chip. So this all we have discussed. Now we will find what is the value of shear strain here, and then we will discuss the relationship among the velocity of the chip, the cutting velocity, and the shear velocity. And from this part you can expect at least 2 questions in the exam, in the objective type questions, both in the GATE as well as the engineering services examination. And previously we had discussed the cutting forces, and after this we will be discussing the merchant circle diagram analysis, the one of the most important part. So if you have any doubt, any questions, please write to me in the comment box, and if you like this video lecture, then please subscribe to my channel and share it among others. So let us discuss this. Suppose you have the material here. This is the shear plane, and when the tool shears the material, this shear plane moves from this position OD to new position BC. Suppose this gap between OD and BC perpendicular, this is delta. Now you can see here, this is the rake surface of the tool. So this is rake angle, this is the vertical line, and this is the relief angle. Workpiece is moving with velocity v or vc, you can write whatever you like, cutting velocity. So here the material, initially it was O, B, C, D. Now as a result of shearing, it becomes, its new position becomes O, M and D. So if you make an enlarged diagram of the shearing of this portion, if I make an enlarged diagram of this portion, this is the vertical line, this is the rake surface of the tool, this angle is alpha, and this point is here, you can say M, and if I draw a line parallel to this NB, this line is parallel to NB. So we will name it accordingly. This is B and this is M, and drop a perpendicular from this point O to MB. This is perpendicular. So this angle is alpha, and this or these two are parallel, so this is also same line parallel, so this represents the shear plane in new position. So this angle is phi, the shear angle. So this angle will be 90 minus alpha, this is phi, this is 90, this is 90 minus phi. So you can write the angles accordingly. This angle O M B, this is equal to, I think this will be 90 plus alpha minus phi. OMB is 90 plus alpha minus phi. You can check it. Now the shear strain, suppose I write this as E. This is defined as, suppose this point is P. I drop a perpendicular from here. This point is P. Length of OP is equal to delta. So we have the shear strain that is defined as this length BM divided by OP, which is BM divided by delta, or E is BM can be written as BP plus PM divided by OP. So BP by OP plus PM by OP. So this gives us BP by OP. What is BP divided by OP? This is cot phi plus PM divided by OP. PM divided by OP. This is equal to tan of phi minus alpha. So this is the expression for the shear strain. So you should remember this. Now we have a question to solve. It is given that during orthogonal machining, remember this is with respect to the orthogonal machining only and not the oblique machining. So for the orthogonal machining, with a cutting tool having a 10-degree rake angle given in the question, alpha is 10 degree. The chip thickness is measured to be 0.4 mm. T1 is 0.4 mm. This is the chip thickness. T2 sorry. T2 is 0.4 mm and uncut thickness is 0.15 mm. Determine the shear plane angle and the magnitude of the shear strain. So we have to find the shear plane angle, means position of shear plane angle. That means you have to find phi, and the shear strain also you have to find. So we know that R here is T1 by T2, 0.15 divided by 0.40, T1 divided by T2, and this is equal to 0.38. So first you can find tan phi using this, R cos alpha over 1 minus R sin alpha. So 0.38 cos 10 degree over 1 minus 0.38 sin 10 degree. So this will give you phi comes out to be 21.8 degree approximately. This is the value of phi. Answer to the first part of the question. And now you can find the second part, the shear strain. E is equal to cot 21.8 plus tan 21.8 minus 10 degree. And on solving you will get this as equal to 2.71 approximately. So friends, this is the answer to the question. Now after this, let us discuss the relationship among the three types of velocities which we come across during the cutting operation. Let us draw this diagram again. This is the shear plane. So we have different velocities. We can show these. The velocity of shearing along this shear velocity, and we have the cutting velocity in this direction VC, and third is the chip velocity V chip, CH chip in this direction. Now this angle, this is rake angle alpha, and this angle is phi. Now we can show these velocities with a different diagram. The shear velocity is in this direction, Vs, and the chip velocity is in this direction, V chip, and we have the cutting velocity in this direction. This is vertical. Chip flows along this rake surface, which makes an angle alpha with the vertical. Shear plane makes an angle phi with horizontal, and horizontal direction is the velocity of cutting. So these are the three velocities represented with the diagram by three sides of a triangle. So this angle is alpha, this whole is 90, this is 90 minus alpha, this is phi, so this angle will be 180 minus 90 minus alpha plus phi, or this is 90 plus phi minus alpha, so 90 plus phi minus alpha. Sorry, alpha minus phi. So now we can apply the triangle law to this. So I can write VC divided by sine of angle between the other two velocities, sine of 90 plus alpha minus phi is equal to V chip divided by sine phi is equal to Vs by sine of 90 minus alpha. So this is Vc sin 90 plus alpha is cos alpha minus phi, V chip by sin phi, Vs shear upon cos alpha. So this ratio of chip velocity divided by the cutting velocity can also be written as Vc Ch by C sin phi divided by cos of alpha minus phi. So if you have a zero rake tool, in that case tan phi is equal to R, and for zero rake tool V chip upon Vc is equal to sin phi upon cos phi, that is equal to tan phi, that is equal to R. For a zero rake tool we have chip velocity is equal to R times of the cutting velocity. So this is the relation among the velocities, and you should know this, remember this result with the help of this diagram, and there may be a question based on this. So you should learn this and remember this, how to find the relation among these velocities, because the question may be asked from this. Generally a question is asked from this part. So in next discussion we will be discussing about the merchant circle analysis for the cutting forces, the forces which are acting on the tool as well as on the workpiece during cutting operation.